Good morning all. I hope you have gone through the notes on characteristic value and characteristic vectors. So today's class we'll look at what are characteristic values and vectors and how to find out the characteristic values and vectors. Now this will be used in the coming classes to find out the solution of system of equations. So today let us define characteristic value and characteristic equation. So suppose you are given the matrix A. So A must be a square matrix. So let A be a given n by n square matrix of real numbers. Then by a characteristic value or eigenvalue of a matrix that is a number lambda such that for which the equation Ax is equal to lambda x has a non-zero vector solution x. So basically the meaning of eigenvalue or characteristic value for a matrix A is, so that is a number lambda such that, so when A is multiplied with a particular vector x, അപ്പോൾ നമ്മൾ A x വെച്ച് multiply ചെയ്യുന്ന, that is equivalent to taking this constant multiple of x. So here the value lambda, this is here you are multiplying a matrix A with an n by 1 matrix. എന്ന് പറയുന്ന n by n matrix ആണ് ഇത്, n by 1 matrix. അപ്പോൾ given a specific x value by eigenvalue you mean that is a number such that നമ്മുടെ മാട്രിക്സിനെ ഈ വെക്ടർ വെച്ച് മൾട്ടിപ്ലൈ ചെയ്യുന്ന, that is equivalent to taking the constant multiple of that particular vector. So such a value lambda is called the eigenvalue, and such a corresponding vector x which satisfies this equation is called the eigenvector or the characteristic vector. So Ax, the lambda is a value such that Ax is equal to lambda x for the vector x. So x must be a non-zero vector, and the vector x is called the characteristic vector or eigenvector. So a characteristic vector or eigenvector of A is a non-zero vector x such that Ax equal to lambda x for some number lambda. And again when you take the equation, so let us see how to find the characteristic values and characteristic vectors. So we have Ax equal to lambda x, so that implies A minus lambda I x equal to 0. Again this is a system of equation in the form Ax equal to 0. We need to find the non-trivial solutions. So x cannot be 0. So we get a non-trivial solution when, so we get a non-zero x when determinant of A minus lambda I is equal to 0, and the equation determinant of A minus lambda I equal to 0 is called the characteristic equation. So upon solving the characteristic equation, So that will give us the characteristic values or eigenvalues. So this is the determinant. So that is a11 minus lambda, then a12, etc. a1n, then you have a21, a22 minus lambda, a2n, so on, an1, an2, and ann minus lambda equal to 0. So this will give us an nth degree polynomial. So this is an nth degree polynomial. So when you solve for this nth degree polynomial, that will give us the corresponding eigenvalues. And we will see a few theorems. So a few results related to the eigenvalues. So the first result is, so suppose each of the n characteristic values lambda 1, lambda 2, etc. lambda n of n by n matrix A is distinct and let x1, x2, etc. xn be a set of the corresponding eigenvectors. Then the result states that then these vectors will be linearly dependent. Then these vectors are linearly independent. So that is the first result. So corresponding to n distinct eigenvalues, you will be getting n corresponding eigenvectors, and these eigenvectors are going to be linearly independent. Now the next result is, so suppose the n by n matrix A has a characteristic value of multiplicity m, where you have 1 less than m less than or equal to n. So that means you have an eigenvalue or a characteristic value which is repeating m times. So m lies between 1 and n. M equal to 1 anangil, that means it is occurring only once. So m must be greater than 1 and it can be equal to n. So all the roots can be the same. Characteristic value not the root in the situation. And then this repeated characteristic value having multiplicity m has p linearly independent eigenvectors corresponding to it, where you have 1 less than or equal to p less than or equal to m. So suppose you have an eigenvalue which is having multiplicity m. Now when you find the eigenvectors, the corresponding number of eigenvectors can be between 1 and m. So number of eigenvectors can be 1, ചിലപ്പോൾ 2 eigenvector ഉണ്ടാവാം, or sometimes it can have m eigenvectors. So that is the case when you have repeated eigenvalues. So that depends on the corresponding matrix, how many eigenvectors it has. So next result is again regarding the multiplicity. So if the n by n matrix A has one or more repeated characteristic values, then there may exist less than n linearly independent characteristic vectors of A. So if matrix A has repeated characteristic values, so when you find the set of all eigenvalues, eigenvalues corresponding to set of all eigenvectors corresponding to these eigenvalues, you may get less than n linearly independent eigenvectors. അപ്പം നമുക്ക് exactly n eigenvectors ഉണ്ടാവണം നിർബന്ധമില്ല. So that may be less than n also. So that depends on the corresponding matrix. And next we'll see result on a real symmetric matrix. So if you have an n by n matrix, so an n by n matrix A of real numbers is called real symmetric if you have A equal to A transpose. So if A is equal to A transpose, matrix is said to be real symmetric. Now when you have a real symmetric matrix, so we'll see at a few results. Then if you have a real symmetric matrix, so all the characteristic values of a real symmetric matrix are real numbers. And one more result. So if A is an n by n matrix, again real symmetric, then there exist n linearly independent eigenvectors of A, whether the eigenvalues are distinct or not. So for a real symmetric matrix, even if the eigenvalues are distinct or not, it will always have n linearly independent eigenvectors.